Okay, so in this video, we want to look at the graphs of exponential functions. So this is section 4.2. Graphs of exponential functions. Okay, so in particular, let's look at the functions f of x equals 3x. So remember, right, in general, exponential function has the form f of x equals a times b to the x. So in this case, a is equal to 1 and b is equal to 3. Okay, and then the other function I want to look at is f of x is equal to 3 to the minus x. But another way of writing this is we can write this as, remember, if you have a negative exponent, you can put that power, right now it's in the numerator, I can stick it in a denominator and it becomes a positive. You change the sign, right, of the exponent. But then this, since x, since 1 to any power is equal to 1, right, it doesn't matter what x is, I could also write this as 1 to the x over 3 to the x. And that's simply 1/3 to the x. So 3 to the minus x is the same thing as 1/3 to the x power, right? They're exactly the same. So in that case, a would be 1, b would be 1/3. Okay, so in this case, a is equal to 1, b is equal to 1/3. All right, so let's get an idea of what these look like. What I'll do is I'll make a little table for each of these functions. So for the first function, right, I have x, and then I have 3 to the x power. And then for the second one, I have x, and then I have 3 to the negative x, but that's the same as 1/3 to the x. Okay, and I want to plug in some points. Let's just use maybe, I don't know, maybe -2, -1, 0, 1, and 2. So those are my 5 points. And same thing here. Those will be my 5 input values. Could do more, but that'll give us a general idea of the shape. Okay, well, what is 3 to the x when x equals -2? Well, that's the same as 1 over 3 squared, right? So this is 1/9. What about 3 to -1? Well, that's 1 over 3 to the 1, so that's just 1/3. 3 to the 0, well, you have to remember anything to the 0 power by definition is equal to 1, right? 3 to the 1 is simply 3, and then 3 squared is going to be 9. And on this side, I'm going to have exactly the opposite, right? So I have, I'll just use the first form. That'll be fine. So I have 3 to negative, and I want x to be -2. Well, that's the same thing as 3 to the +2, so that's 9. 3 to -1, that's going to be 3 to the 1, so that's 3. 3 to the -0, right, it's the same as 3 to the 0, so that's 1. 3 to -1 is 1/3, and then 3 to -2 is 1/9. Okay, so if we plot this, and let me do that on Desmos, and I'll paste it back into this lecture. Okay, so in this case, the red graph is f of x equals 3 to the x, and the blue one was f of x equals 3 to the minus x. So notice, right, as, well, a couple of things, right? as x goes to infinity, as x, goes to infinity, so as x gets really, really large, what happens to 3 to the x? It's also going towards infinity, right? So as x gets really, really large, as they move to the right, the red function gets super, super, super large very quickly. But what happens to the other function as x goes to infinity? So if I look at the blue curve, which is 3 to the minus x, as x goes to infinity, that graph is going towards 0, right? So it gets really, really, really small. So 3 to the x grows rapidly, right? So I can say f of x equals 3 to the x grows rapidly as x increases, and f of x equals 3 to the negative x decays rapidly as x increases. Okay, there's another thing that you'll notice here is that these graphs are reflections of one another about the y-axis, right? If one is just a reflection of the other about the y-axis. And remember, that makes sense because if I had some function, right, let's say, I'll just use the 3 to the x one. And remember, instead of x, if I make that a negative x, then that should give me the reflection. But in this case, if I plug in negative x where I have x, I'm going to get 3 to the negative x. So these are reflections. So they're basically horizontal, I'll say horizontal reflections of one another. Okay, so let me give you some like general features of the graph of an exponential function. So that was just a particular example where we used b equals 3 or b equals 1/3. So in general, so I'll say general features of the graph of an exponential function. And we'll just use the form, f of x equals a b to the x. Okay, so first thing, the a is really the vertical, it's the y component of the vertical intercept, right? So we could say that, if I plug in 0 for x, what am I going to get out? Well, in this case, right, if I do f of 0, I'm going to get a times b to the 0. But remember, b to the 0 is equal to 1. So this is just equal to a. So 0a is the vertical intercept. The b determines the rate at which the graph grows. So b determines the rate at which the graph grows when a is positive. So we're going to assume a is positive first. So when a is positive, the function will increase if b is greater than 1, and it'll decrease. So like in our example, we had b was 3, right? And it increased very rapidly, right? As x got larger, it increased really, really, really quickly. And then it'll decrease, the function will decrease if b is a fraction. And the way we can write that is if b is greater than 1 and less than, greater than 0 and less than 1, right? So if it's a fraction, like, again, in our example, let me write that 0 better here. In our example, 3 to the minus x, that was the same thing as 1/3 to the x. So b was 1/3, right? It was between 0 and 1. And we saw that the function, the graph decayed. Now, what else do we know? The line, the horizontal line y equals 0 is a horizontal asymptote, right? Because the graph got closer and closer and closer to that line. It approached 0 but never quite reached it. So y equals 0 is a horizontal asymptote. Now the a, if the a is greater than 0, and that's the case we're dealing with so far, so a is positive, so if a is greater than 0, the graph is concave up. Regardless of what the b is, right, the graph will be concave up. And if a is less than 0, so if a is negative, the graph is going to be concave down. In that case, it's going to be like flipped about the x-axis, right? Like a vertical flipping of the function. So if a is less than 0, so if it's negative, the graph is concave down. Okay, and then a few more things that are true. So if b is greater than 1, so that was the one that as the input get larger and larger and larger, the graph grew faster, 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 so it's getting larger and larger and larger. So we could say as x, for that particular graph, as x approaches infinity, then the function also approaches infinity. So I'll say, like, for an example here, this was like our f of x equals 3 to the x. So look back at that graph. And then if we go the other way, as x approaches negative infinity, what was true about this graph, the 3 to the x? The function approached that line y equals 0, right? So it's approaching 0, right? It's approaching that horizontal asymptote. And then if b was a fraction, so greater than 0 and less than 1, so again, the one that we looked at was f of x equals 1/3 to the x, which is the same as 3 to the minus x. So if that's the case, then as x goes to infinity, the function approaches 0. Right, so it decayed. So as the input gets larger and larger and larger, or as x gets larger and larger and larger, the function decays. It gets closer and closer and closer to 0 from above. And then as x goes to negative infinity, so again, look back at that graph, 3 to the minus x. As that goes to minus infinity, the function blows up again, right? It gets larger and larger and larger. So f of x goes to positive infinity. The other interesting point is, given that general function, the graph will always pass through the points zero a, right? So that's the vertical intercept. And then if you plugged in 1 for x, you're going to get a times b to the 1, but that's just ab. So that this point will also always be on that graph, right? If we have that function, the general exponential function of a to the b x. So I plug in 1 for x now, I'm going to get f of 1 equals a times b. Okay, so it has to pass through those 2 points. Okay, so here's an example. Let's say we're asked to sketch a graph of, let's say, f of x equals 3 to the 1/2, 3 times 1/2 to the x. Say we want to sketch that particular exponential function. Okay, well, we know, right? We know that this graph would have to go through the point 0, 3, right? Always has to pass through 0a. Or, I mean, if you don't see that, just plug it in, right? If I do f of 0 here, I have 3 times 1/2 to the 0. But remember, 1/2 to the 0 is 1. So this is 3 times 1, which is 3. And it also has to go through the point 1, a times b, right? So in this case, it'd be 1, 3/2. Again, if you don't see that, plug it in, right? If I plug in 1 for x, then this is going to be 3 times 1/2 to the 1. But what's 1/2 to the 1? That's just a half. So this is going to be 3 over 2. You can think of that as 3 over 1, right? So 3/2, or 1.5. So if we plot this, this is x, this is y. Actually, let me move this a little bit up. So that's y. So it definitely has to go through the point 0, 3. So right there. And it has to go through the point 1, 3/2. So let's say 3/2 is like right here. Since the b is a fraction, right? It's between 0 and 1. We know it's going to decay. And in fact, the only way it can do this, right, to actually go through those points is going to look something like this. And this will come through here, and then it'll get closer and closer and closer to the line y equals 0, which is really the x-axis. So it'll look something like that, right, if you sketch it out. Okay, another thing that you'll notice in general, actually let me make some pictures and I'll copy them in here so you can see this. Okay, so on this graph I have a lot of functions that are plotted, and in particular, so this purple one right here, this is f of x. Let me go back to, this is going to be f of x is equal to 1.5 to the x. So my b is 1.5. The green one is f of x is 2 to the x. The black is e to the x, right? So remember, e is like 2.7-ish. And then the blue one above it is 3 to the x. And then on the other side, it's going to be 1/2, 1/3, right? 1 over e. But the easier way to write this is think of this as 1.5 to the negative x. So that would be the green one. And then this would be 2 to the negative x. That's the blue. Then this would be e to the negative x. And then this would be 3 to the negative x, right? So those are decay. So the ones that have 1.5 to the positive x, those are the ones that are growing. So exponential growth, right? And then the ones that have the negative, right, negative x, are decaying. So notice what's going on here. The larger b is, so the larger b is, the steeper the graph. So it's going to grow faster or decay faster. Do you guys see that? So like this one, remember this one right here, the purple, if you fall all the way from here, it's pretty much 0, right? Then it gets increases. All of the graphs are going through 0, 1. Because if I plug in 0 for x for any of these functions, anything to the 0 power is equal to 1, right? So they all go through 0, 1. And then now this one is increasing rapidly, but definitely not as fast as the 2 to the x, which isn't as fast as the e to the x, which isn't as fast as the 3 to the x, and so on. So as b gets larger, the graph grows more rapidly. Or on this side, if we have 1.5 to the minus x, it's decaying, and then as b gets larger, it decays more rapidly. Okay, and you can certainly see that over here too, right? This is going down really quickly, and it's approaching 0 very, very quickly. Okay, let's talk a little bit about transformation of exponential graphs. So if we shift these. Okay, so in this case, the graph that I plotted in blue is just a graph of f of x equals 2 to the x. So this is just, this is just f of x equals 2 to the x. And then the red is f of x equals 2 to the x minus 2. So remember back when we talked about transformations. This is way back in chapter 1, right? I think it was 1.5 was the section. If I subtract 2 from the x, from the input, what does that do to the function? Well, it shifts it to the right? In this case, 2 units to the right. So shifts to right. So the red graph is shifted to the right by 2 units. But the other way to think about this is it really just changes the initial conditions, right? It changes the a. So for that original graph, right, where it was 2 to the x, the a is going to be 1, right? Because remember, the a represents the y coordinate of the vertical intercept. So like that green point right there has the value 0, 1. Where in this case, the red one has an intercept of 0, and this is going to be 1/4. So it kind of looks like shifting to the right is just changing that initial value. And that actually is the case. Let me prove why that's the case, okay? So again, we had 2 to the x minus 2, right? But remember if you're using your rules of exponents, right? If I have like y to the a times y to the b, remember that's equal to the y to the a plus b, right? Those are my rules for exponents. So I could break this up. I could think of this as this being 2 to the x times 2 to the negative 2, right? Because if I go the other way, if I multiply those together, I have to keep the base 2, and I have to add the exponents. Well, x plus negative 2 is the same as x minus 2, right? So I can split it up like that. But what is 2 to the minus x, right? What is this value right here? Well, 2 to the minus, sorry, I said 2 to the minus x is 2 to the minus 2. So 2 to the negative 2 is 1 over 2 to the positive 2, right? If you bring that down to the denominator, you have to change the sign on the exponent. And then 2 squared is 4. So this is the same as 1/4. So really this function I could also write as 1/4 2 to the x. So my a, remember this is my a here, has changed from, well, when it was just 2x, right, the a was 1, and that's what we're seeing on the graph here, right? We're seeing 0, 1. So that's this point right here, 0, 1. And then now the a is changing to 1/4. So a horizontal shift you can think about as just corresponding to a change in the initial value of the function. Okay, so let me write that down at the bottom here. So a horizontal shift corresponds with a change in the initial value of the function. Okay, what about a vertical shift? So now, let's say I want to consider, actually here, I'll do this on a new page. So now I want to consider f of x is equal to 2x. I'll just use 2x again. But now I want to subtract 3 from that. So again, remember back to our transformations, right, in section 1.5. If I subtract something from the original function, what does that do? It shifts that original function down, right, by 3. If I add, it shifts up. So it's a vertical shift in this case, right? In this case, it's going to be shifted down by 3. So let me... Okay, so what happened in this case? Well, so this is the function in the red, right? This is f of x is equal to 2 to the x. And then it just shifted down by 3, right? So minus 3. So instead of having a horizontal asymptote at y equals 0, we now have a horizontal asymptote at y equals negative 3. So that's the only difference, right? It shifts down. So now I'll say there's a horizontal asymptote at, and it is of this line y equals negative 3, right? So that's the dashed line right there. So it just took that original function 2 to the x and shifted it down. Okay, so in general, So in general, any transformed exponential function can be written in the form f of x is equal to a b to the x, and then I will also account for the fact that it could be vertically shifted, so I'll do plus c. Okay. Now, what's going to happen in this case? Well, now y equals c will be the horizontal asymptote. So y equals c is the horizontal asymptote. And the vertical intercept which originally, right, is at 0a, is now shifted to 0, comma, and now the y coordinate is going to be, instead of a, it's going to be a plus c. Okay, so for an example, let's sketch a graph of the following function. Actually, I'll do this on another page as well. So let's say I'm given this function and I want to sketch it. So I'll say sketch a graph of f of x equals, let's say, 3 to the 1/2, or 3 times 1/2 to the x minus 2. Okay, so again, a couple of things. We know that, first of all, is this exponential function growing or decaying as you read left to right? Well, the b tells us that, right? Since the b is equal to 1/2, it's decaying. So as I go from left to right, it's got to be going down. What else do I know? I know that I have a horizontal asymptote right? And that line, the horizontal asymptote of the line, is going to be the line y equals -2, right? Because remember, it's y equals c. And I also know that the vertical intercept is going to be at the point, actually in this case, what's a? A is the 3, right? So 3, b is 1/2 to the x, and c is -2. So the vertical intercept, remember, is going to be shifted now to 0, comma, a plus c. So in this case, it'll be 0, comma, 3 plus a -2, but that's just equal to the 0, comma, 1. Right, so that point is going to be 0, comma, 1, the vertical intercept. So now we can sketch the graph, right? That should give us plenty of information. So just as a sketch, so this is x, this is f of x. Again, we know that there is a horizontal asymptote, right, of y equals -2. So I'll just dash this in here. So it's got to approach that line. right, as x gets really, really large. I also know that the vertical intercept is now at the point 0, 1. So something like this. And I know that the graph decays, right? So it's going to start as x gets really, really small. It's really, really, really big. And then somehow it's going to go through here. It's going to decay, and then it's going to get closer and closer and closer to y equals -2. So it'll look something like that. Okay. Let me show you an exact picture of this. Okay, so here is the actual graph, right? So actually we did a pretty good job, right? So it looks like it goes through the point 0, 1, just like we expected. So I drew that in green there, the dot in green. It's decaying, right? So as x gets large, it's getting really, really small. And in this case, it's approaching the horizontal asymptote of that line y equals -2. Right? It's getting closer and closer and closer to that line as s gets larger and larger and larger. So it's approaching, the function is approaching -2 as x gets really, really, really large. Okay, let's see if we can go the other way now. I'm going to give you a graph, and let's see if we can find the exponential equation. So I want to find an equation for the exponential graph, which I'm going to draw in a second. Actually, I'll have Desmos do it again. Okay, so here's the graph, and given this graph, we want to come up with the exponential equation, right? We want to come up with the function, the exponential function. Well, what do we know? If you look at this, first of all, it looks like it's flipped, right? It's flipped over that line y equals 1. So that means the a, the thing out front, is going to be negative, right? Because it's concave down now, so it's flipped. But we can figure all that out later. What else do we know? We know that there is it looks like a horizontal asymptote. And it's the line y equals 1, right? That blue dashed line. So that means, remember, that tells us what c is. So if we have the general form of our exponential function, it's going to be a b to the x plus c. So this tells us that c must equal 1, right? So we know that c equals 1. What else do we know? Well, we actually know 2 points that the graph passes through, and I highlighted those in green. So it passes through this point right here, which is -2, 0, and it passes through this point, which is 0, -3. So if I know that c equals 1, and I know 2 points that the graph passes through, then I can use those 2 points, right? I can plug those 2 points in because they have to satisfy the equation. And that will allow me to find a and b. And then once I have a and b, I'm done, right? I have my equation. Okay? So here, let's see how this is going to work. So let's say, move this up a little bit. So again, I have f of x is equal to a times b to the x plus c. Okay? Let me just call this y to make it easier. So y equals a b to the x plus c. And I know that c is 1, right? C is a positive 1. Again, that comes from the horizontal asymptote. Now, let me plug in my point. So -2, 0. So that means y is 0 when x is -2. And again, I know that c is equal to 1. And then the other one is 0, negative 3. So y is negative 3. When x is 0. Well, this is going to allow me, the second equation there will allow me to find a, right? So if you think about this, I have negative 3 is equal to a. What's b to the 0? Well, anything to the 0 power is 1 plus 1. So this is just negative 3 is equal to a plus 1. And then if I subtract 1 from both sides, I'm going to get a is equal to negative 4. And I thought it was negative because it looked like it was flipped vertically, right? So we have a. Great. Now we need to go back and find b. Okay? So let me plug this into the first equation, right? Now that I have a, let me go back and plug it into the first equation, that equation. So if I do that, I'm going to get 0 is equal to negative 4 times b to the negative 2 plus 1. Remember what b to negative 2 is, right? I could write this as negative 4 over b squared plus 1. So then I could solve this for b, right? So there's a couple of ways you could do this. Let me just multiply everything by b squared just to clear out the fractions. So I have b squared times 0, and on the right hand side I have b squared times negative 4 over b squared plus 1. So I have to distribute in that b squared. So I'm going to get 0, right, is equal to, well, b squared times negative 4 over b squared is just negative 4. And then b squared times 1 is b squared. Now if I bring the 4 to the left hand side, I'll add 4. So then I'm getting b squared is equal to 4. And then how do I get b? I need to take the square root, right, of both sides. And you have to remember it could be positive or negative. However, remember we said earlier that b, we had to make sure it was always positive. So what is b going to be in this case? It'll be 2. Now we're done. Once we have a, b, and c, we're done, right? So now I can write out the actual function, the exponential function of that graph. It was f of x is equal to negative 4, that was a, right? Then it was b, so that's 2, raised to the x, and then plus c, but c was 1. So this is the function that describes that graph. So we got c from the horizontal asymptote, and then we used 2 points on the graph to figure out a and b. And by the way, the vertical intercept, so this point right here, right, the 0, 3, that's always a nice point to use, the vertical intercept. Why? Because if I plug x equals 0 into the equation, what's always going to happen to this term? Well, b to the 0 is always going to give me 1. So that will easily allow me to find a. Okay, and you'll get more practice with some problems like that. All right, great. That's it for section 4.2. And the next video lecture, I will start logarithmic functions, which is section 4.3. Thanks.